Thanks for watching. In this presentation, we present KCR. KCR combines the task knowledge of a source dataset with stronger rotated annotation and the domain knowledge of a target dataset with weaker axis-aligned annotation. This enables the model to predict rotated detection on the target domain. This approach combines the advantage of both weakly supervised learning and transfer learning. If we look at this image on the left-hand side, we have axis-aligned detection. It is very hard to see which bounding box belongs to which banana. On the right-hand side, we have rotated detection. The bounding box is much tighter and more precise. We can very easily tell which bounding box belongs to which banana. However, rotated annotation is more expensive and it's not available in many annotation tools. So in this paper, we aim to address this problem. We enable the detector to learn from axis-aligned annotation, but it will be able to predict rotated bounding box in the inference. So this is our intuition. If we look at this pair of images, what is in common? We can see that the common is the kicking action. So we can divide in knowledge to be like a skill knowledge and the domain knowledge. The skill knowledge is the kicking part in this case. Domain knowledge is different from two images, which is a ball and a chair. A person that learns how to kick a ball is very easily to transfer the skill into a different domain, which is kicking the chair. So we follow this intuition and develop this framework. So in our paper, we take the assistance of a public source dataset, which is free. The source dataset has rotated annotation on a different set of objects. Then we also have a target dataset that only has axis-aligned annotation for training. As we can see, if we combine the domain knowledge and the task knowledge of a different dataset together with KCR, in the test time, the model will be able to predict rotated bounding box. And it doesn't require expensive annotation. I would like to briefly show the rotated detectors that we are using. So this is not our contribution. We use this detector, which is ORCNN. It's a two-stage detector. We choose this detector because the first stage, as we can see, it has 6 parameters. It is very easy for us to do projections because we project the rotated bounding box to axis-aligned one. So this formulation is particularly beneficial. Here we have an overview of our detailed approach. We mainly use co-training strategy. In the training time, we have a batch of target image and a batch of source image. So the batch size is essentially multiplied by 2. And the parameters between two models are shared. We use the co-training and also the projection assignment and losses. The idea is that we want the model to learn as much as possible from the domain data, from the target data set, which has domain knowledge, but we want to minimize the boxes that it's learning. So we wanted to learn what's a cucumber in this case, but not the box. Here is the result of our work. We can see that in many cases, KCR enables the detector to have a competitive performance, which is almost on par with the fully supervised learning. This is visualization. So with the axis-aligned training datasets, we can see that the model can only predict axis-aligned datasets. But with our work, the model is capable of predicting rotated bounding box pretty tightly. We also apply KCR to this fresh produced fresh produced data set. We can see that KCR enables detector to learn from axis aligned annotation and capable of producing predicting rotated bounding boxes in the test time. And it's capable of mitigating like large domain gap between source and target data set. Thanks for watching.